All right, welcome back to our discussion on Taylor series. So what we learned last time is that if f of x is a power series centered at x equals a, then the nth degree coefficient's general form is just the nth derivative of the power series evaluated at a divided by n factorial. And again, a power series centered at x equals a is just something that takes this form, right? So it's a function, it's a series, it has coefficients in front of each term, and each term is just of the form x minus a to the n. Why? Because we're centered at a here. So then a would be what you'd have to plug in to wipe away all the terms of higher degree. And so this is an example of a power series centered at a. So what does Taylor's theorem give us? Taylor's theorem gives us a way that given a power series, we can systematically compute its coefficients. But more importantly, if we're given a function that's not a power series, we now have a systematic way to form a power series from it. And that is super potent, because if we're given a function, we should be able to compute its derivatives, evaluate it at a, and then divide by n factorial. And if we can do that, we can cook up a collection of constants that are going to be the constants within our series associated with our function. So what's our function of interest here? Let's work this example. Imagine we're looking at the function sine of x. Now we want to find a power series specifically using Taylor's formula. So we're going to find a Taylor series for our function, and it's going to be centered at x equals 0. Okay, so let's go through the process, because we need to ultimately cook up its coefficients. And how do you cook up the coefficients? By taking derivatives, evaluating at the center, and dividing by n factorial. So first, let's take derivatives. The 0th derivative is going to be taking no derivatives. That's just sine x. The first derivative, cosine. Second derivative, derivative of cosine. Third derivative, derivative of minus sine. Fourth derivative, derivative of minus cosine. In fact, if you notice here, there's going to be a trend going down, right? This is essentially something that cycles back every 4 derivatives, from sine to cosine to minus cosine, and back to sine again. We're going to exploit that as we come up with our Taylor series. Now, we have to evaluate at the center. What is the center here? The center is 0. We're interested in our Taylor series centered at 0. So what do we need to do? We need to evaluate each of these things at 0. So I'll write out the first couple just so that we can follow along nicely. We need what sine of 0 is. That turns out to be 0. We also need what cosine of 0 is. That turns out to be 1. Minus sine of 0 is also 0. Minus cosine of 0 is minus 1. Let's see, sine of 0 will be 0, and in fact, this will recycle, right? We've already discussed this. So the cycle will be 0, 1, 0, minus 1, repeat. 0, 1, 0, minus 1, repeat. 0, 1, 0, minus 1, repeat. Right, but now, these are not the coefficients of our power series. These are just the numerators of the coefficients of our power series. We also need to divide by n factorial. So we need to divide by 0 factorial here. I should be really careful, because as I say the statement divide by 0 factorial, that sounds like you're dividing by 0, but in order that we're not dividing by 0, we define 0 factorial to be 1, because in fact, this jives with our previous conception of what what we needed the terms to be here, in the sense that if you take the 0th derivative and evaluate it at a, you'll just get the constant term. So we need n factorial to be 0 in order for that to make sense. So no sweat, 0 factorial is 1. So if we take 0 divided by 1, we're going to get 0. So let me write this out just so that we're all on the same page. 0 divided by 0 factorial is 0 divided by 1. Next, we have 1 divided by 1 factorial. So, that's going to be 1. Then we have 0 divided by 2 factorial. We have minus 1 divided by 3 factorial. And then we have 0 divided by 4 factorial, and so on. And this is going to continue forever. Now, what are each of the numbers that had popped up in the last column here? Well, based off of Taylor's theorem, these are the coefficients of given degree. So this is our degree 0 coefficient, our degree 1 coefficient, degree 2 coefficient, degree 3 coefficient, degree 4 coefficient, and so on. So we can write ourselves a Taylor series associated with this function, associated with the function sine x, which is pretty cool, I think, because now we're writing sine x in the form of a series, which you might not have ever thought of sine x as being a series, but hey, we're writing it as such here. So let's see, f of x equals sine x. Well, if we were writing this as a series, we could write in the form of what? F of x equals, we will have no constant term. We will have 1 for our degree 1 coefficient. So we'll have 1x. 0 degree 2 term, we'll have a minus 1 over 3 factorial on our degree 3 term. Our degree 4 term will have no coefficient. Our degree 5 term will actually be back up here, but divided by 5 factorial, that's going to be plus 1 over 5 factorial, x to the 5th. Because remember, there's a recycling of our terms in this column, but then we are dividing by the subsequent factorial to get to the next column. So ultimately, below, our sine would be a cosine of 1, which would then over here, when we divide by n factorial, would be 1 divided by 5 factorial. And that's where this 1 divided by 5 factorial comes from. The next would be minus 1 over 7 factorial, x to the 7. And this goes on forever. So now thinking about what this is, I claim if we work a little bit, we could actually express this in sigma notation. We could write this as what? A sum from n equals 0 to infinity. And looking at our coefficients here, the coefficients are either, let's see, upstairs we got a 1 or a minus 1, depending on whether or not we are at an even factor or an odd factor. So putting this all together, I believe, downstairs we get, 2n plus 1 factorial. So n equals 0, we'll get 1 factorial downstairs, because remember, this first term was like 1 divided by 1 factorial. N equals 1, we'll get 3 factorial downstairs. N equals 2, we'll get 5 factorial downstairs. N equals 3, we'll get 7 factorial. We also need our signs to alternate, so we need a positive 1 and then a minus 1 on our next term. In order to do that, we'll incorporate a power of minus 1, because powers of minus 1 are just pluses or minuses according to whether or not you have n being even or odd. And then ultimately what? This will be x to the 2n plus 1 power, because the power of x is precisely the value that's in front of the factorial, that's in the downstairs of the coefficient. So ultimately we had 1 over 1 factorial x, 1 over 3 factorial x to the third. So here we've got this power of 1 over 2n plus 1 factorial x to the 2n plus 1. Long story short, we've actually taken our series representation of sine, and now we have written it out in full sigma notation, which is pretty cool. Having said all of this, I want to make one final point in this video, and that is this computation related to the sine function and formulating this series was literally centered about the value x equals 0. When we got down to this middle column and we're plugging in the value of the center, that was a necessary piece of the puzzle to get this series, because this series is associated with sine when we center at x equals 0. However, if we center at a different value from x equals 0, like, for example, if we take the same function but center at x equals pi over 2, the question is, do we get a new series? Well, let's run the numbers. We know what the derivative, the zeroth derivative of our function is. That's taking no derivatives. The first derivative, cosine, negative sine, negative cosine, positive sine, and then we recycle, right? We've seen this happen. Now, here we plug in a, which is our center, which is not 0 in this case, but rather pi over 2. So when we plug in pi over 2 here for our a, that's going to give us different values out. Because instead of sine of 0 like we did above, here we're going to have sine of pi over 2, cosine of pi over 2, and so on. Now sine of pi over 2, as it turns out, happens to be 1. Cosine of pi over 2 is 0. Negative sine pi over 2, negative 1, and 0, and 1, and so on. And in fact, there will be a recycling here, right? Because we saw this. A cycle of length 4, right? In this case, 1, 0, minus 1, 0, 1, 0, minus 1, 0. But now we're not done yet because we got to figure out what our coefficients are. How do we get those? Divide by n factorial. So here we got 1 divided by 0 factorial. We've got 0. Then we've got negative 1 divided by 2 factorial and a 0. A 1 divided by 4 factorial, and so on. You can see what the next coefficient, the next non-zero coefficient would be from this pattern. It would be, whoops, let me not get off the page there. It would be 1 over 6 factorial with a minus in front of it, right? And you can see how these terms would correspond. Well, that means that we could take our function here, which is sine x, and instead of writing it as a power series centered at 0, we could use a power series centered at pi over 2. So our first term, our first constant term is 1, because remember 0 factorial is 1. So this ultimately comes out to be 1. The next term of interest is 1 over 2 factorial. But now this is not just going to be x squared. We're centered at pi over 2. So this is going to be x minus pi over 2 squared. Next, we're going to have plus 1 over 4 factorial, x minus pi over 2 to the 4th. And this pattern will continue. Minus 1 over 6 factorial, x minus pi over 2 to the 6th, and so on. So if we take this one final step, we could put this in sigma notation, which it will be sort of similar to the previous. Although downstairs, we want a 2n factorial instead of a 2n plus 1 factorial, because downstairs we only have even numbers down below. Remember, this first term is going to be 0 factorial there down in the denominator. So what, n equals 0 would give us that, n equals 1 would give us the 2 factorial, and so on. What's upstairs? Upstairs is also alternating signs, positive and negative. So this is going to be minus 1 to the n upstairs. And then the power of x is precisely the value of our factorial downstairs, which would give us this expression. And what I have forgotten is to subtract the pi over 2. Let me subtract the pi over 2 because that's a necessary piece of the puzzle. So here we go. What do we have here in this, this box? We have a power series expression for the sine function that instead of being centered at 0, 0 would wipe out all the terms of degree 1 and higher, we're centered at pi over 2. And right, what's really cool about this, I think, whenever you reflect upon this is, here's a function which you've seen for years, the sine function. You can center at 2 different values and get yourself 2 different series which are built upon the function value and its derivative values at the particular point of interest that you are centering your computation about. So we have 2 series which are both equal to the sine function, which have slightly different forms because they've been centered at different values, which what that means exactly is going to take some time to inspect and learn. And that's going to be something that you might want to take a look at some of the videos that are on the weekly agenda for you that follow this, because I think there's going to be some interesting insight from them. And actually, we will dive further into this and the implications of centering a series at a particular point whenever we get to Taylor polynomials next week on Monday. But for now, you are armed with the ability to form a Taylor series associated with any function by taking that function's derivatives, evaluating them at the center, dividing by n factorial, and then collecting all the terms, which is a pretty powerful, potent process whenever you think about it.